Yeah, the syllabus has a slightly different, has an extra deadline in there for the project, but that's because the way we did the course conference last year had one more step in it where there was some refereeing, and I decided that was pretty complicated and we're just not going to do it this year. So I'm simplifying things a bit. So there's 2 deadlines you have to know about. The final project is due May 2nd. And for the course conference, which will be April 26th and April 28th, you need to send 2 slides, PDF only. And I think you'll send them to Jisoo. I'll find out how they want to get them. And then they're going to paste them together into one giant file so that on Tuesday and Thursday, they'll have a projector. You'll have the projector ready with the computer, with all the files, and you just come up, do your 2 minutes, and then the next people come up and so on. So that's how it'll work. There'll be prizes. It'll be very exciting. Yeah?
So maybe this is what you're talking about, but in the syllabus, is something due like 2 Mondays from now?
Yeah, so that was because we had a refereeing stage before. There'll be no refereeing this time. Yeah. The refereeing was interesting. Brian wanted to do that last year because he thought, that's how it would just be sort of like experience for you guys for refereeing conferences and that. But it just was kind of a big mess, and it was kind of complicated, so you can ignore that deadline. So these are the only deadlines here. And of course, there's the last assignment as well. Any questions about that? All right, great. So then let's talk about graphs again. Get this out of the way. So we had just written out the log linear model for the simplest case where there was just 2 binary discrete variables, x1 and x2. And we saw that the advantage of the log linear model was that it allows us to use the parameters to talk about conditional independence, or actually dependence in that case. So we started to write down the general case where now I have D features. And again, for simplicity, we're keeping them binary, but that's not necessary. And the probability function looks like this. So x here is a vector. And this is like a series of bits. It's either 0 or 1. This is the probability that somebody has a feature 1 equal to 0, feature 2 equal to 1, and so on. So you can think of it again as a giant multinomial. This is for every possible setting of these things, this is just a number, and there's 2 to the d such numbers. So we can think of it as a multinomial with 2 to the d entries. And the likelihood would just be the corresponding probabilities to the corresponding counts. Let's call a particular configuration here. There's 2 to the d of them, remember. So I'm just going to call it squiggle and C swiggle. I'm just every possible configuration, you have how many times that configuration happened and its probability. It's just a multinomial likelihood function. But what we talked about was taking the log of this, and we can always rewrite it as some constant. It's not locked, is it? Not that that's a bad idea. I don't think it's locked, actually. But that's good. We shamed you anyway, so. And this is the second order interactions and so on. Okay? And we should think of this as if this is the set of all multinomials, all vectors p. And remember, there's always a restriction, right? I didn't mention this. Someone asked me about this at the end of class last time. Of course, the p's have to be positive and add up to 1, and that implies that the betas have some sort of restriction too. Okay? But this is just mapping, let's call this B, every vector P to a vector beta, and we saw we can go back and forth. But it's better to think of it in terms of the betas. And what we saw in the simple case with just two variables, that beta 1, 2 was 0 if and only if x1 and x2 are independent. Now, now comes the big thing about the general case. Let's ignore the fitting issue for the moment. Suppose I told you the true betas. Suppose somebody came along and said, here's the betas. Can I read off the conditional independent statements? And the answer is yes, is that this statement here is in Theorem 7, which is not hard to prove from this representation. But here's what it says, that xj is independent of xk given all the other variables. I'll just say given the rest, if and only if beta a is 0 whenever j and k are in A. So what does that mean? That means, suppose I want to know if variables 5 and 7 are conditional independent given the rest. You might wonder about other conditional independent statements, but for now we're just going to talk about these global Markov properties, as they're called. Are variable 5 and 7 conditional independent given the rest? All you have to do is check, in any of the non-zero terms, do 5 and 7 ever appear together or not? So let me give you an example of that to make that clear. Suppose I just have I have 3 discrete binary variables, or if you want to think about it again as one variable taking 2 to the 3 values, 8 values, a multinomial with 8 categories. And so I know I can write out this probability function, and suppose I tell you it has the following form. It's of the form beta 0 plus beta 1 x1, beta 2 x2, beta 3 x3. Then some of the terms are 0. So when I leave a term out, it implies that the beta is 0. So this is beta x1, x2. So in other words, by writing out the model this way, what I'm telling you is notice that these terms are missing. Right? They're 0. So notice something. The pair 2 and 3 never appear together in here. So what that tells you is that implies that x2 and x3 are conditionally independent given the rest of the variables. Now, the rest of the variables in this case, there's only one other variable, right? So it's just given x1. But if there was 20 other variables, it would just be x2 and x3 are independent given the rest. What that would mean is, in the graph, we don't connect x2 and x3. That's what's telling you when to connect or not connect the graph. Actually, we're getting a little bit ahead of ourselves because I realized maybe I should have talked about this after I talked about Markov properties of graphs. But anyway, this is just the way you read off conditional independence from a log linear model. And so the beauty of this is when you run, if you just put some discrete data into R, and I'm sure there's a similar function in MATLAB, and say fit the log linear model, it's going to give you a bunch of beta hats, and we'll talk about different approaches, but you can test, for example, whether the beta hats are 0 or not, or you can run forward stepwise regression, which will leave out some of the betas for you, just like we did with ordinary linear regression. The final model will have some beta hats in it, but it'll have a lot of beta hats that might be 0. And so you can immediately look at this and say, oh, okay, I know the graph now. The graph looks like this: x1, x2, x3, and x2 and x3 are conditionally independent, so I don't connect those. That anytime, because the 2 and 3 never appear together, I just leave out those two things. So it's a very easy way to interpret the multinomial, and it's a very easy way to determine what the graph is. And so that's the value of using this log linear representation of the multinomial. people call them log linear models, but they're not really models so much as reinterpretations of the multinomial model. Reparameterizations, I guess, is the way to put it.
Is multinomial the only distribution that can be expressed in this?
Yeah, because we're talking about we're assuming all the variables are discrete, so the most general possible model is the multinomial model.
What if they're not discrete? I mean,
Well, then, then we have a whole different problem. So if they're normal, we had the Gaussian graphs. If they're multinomial, we have these. What if some of them are discrete and some of them are continuous? Now it gets more complicated.
no, I mean,
Oh.
if all are continuous, this form looks like something like the exponential family or something.
You mean like it's a restricted multinomial? Because every discrete distribution is a multinomial, unless it's restricted.
For other continuous distributions, is it possible to express some of those distributions?
Not necessarily. No. This is all about the multinomial. Yeah.
So can you actually prove that when the beta is 0, this conditional independence holds?
Yes.
So
This is if and only if.
how do you prove it?
Oh, it's not very hard. In fact, maybe I should have made it a homework exercise. But it comes from the properties it comes from this expansion. And so then you can check that when those things are 0, you have to check now that P of x1 and x2 given x3 is equal to P of x1 given x3 times. So it just directly from the definition.
You can factorize it somehow.
Yep, it's from the factorization. Yeah.
That statement on page 14 about log linear representation, decoding independent statements in terms of these parameters, that's true in general for any log linear model, right? Not just discrete.
No, this isn't even defined necessarily. Because we're talking about the probability mass function. I guess you're asking about what if I took a exponential representation of some arbitrary distribution. I guess that's true. It would still, I think it would still be true as long as the density was positive or something like that. Yeah. But I'm talking about multinomials here right now.
I think the expression here can be written differently if you change the order of the xi.
No. Well, it would, yes, the labels would be different, but the conditional independent statements would be the same.
It seems that we are trying to remove edges from a complete graph. Is that right?
So we'll get to this when we talk more about conditional independence, but these graphs are not statements about edges. Graphs are statements about the absence of edges.
Okay.
The information in a conditional independence graph is in the absence of an edge.
So I'm wondering, from here, it seems that we are building from the lower order terms and then we rise up to the higher order terms. What if we only have the higher order terms and then there's no...
Good question. So we're going to get to that, which is, you might notice if I'd wiped out this term, nothing would have changed, for example. So this gets to the different types of log linear models. We're going to get to that in a minute, actually. That's what the picture in the bottom of page 16 is about. So let me make a technical comment first, which is everything here was binary. If they weren't binary, what would happen? What would happen is that for each, like let's suppose x2 didn't take 0, 1, but it took 3 values, you're going to need more than one term in the sum to handle that. So what will end up happening is you'll have sets of terms corresponding to the variables. It's just a technical complication, but conceptually it's the same thing. So I'm not going to talk about that in the class, but it is explained here on page 15. But it just means that for each variable, instead of there being one beta, there's sets of betas for that variable. Okay, but it's not worth spending time talking about it. Okay, now getting to the question that was just asked. There's actually some issues here about different types of log linear models, and it's explained with this picture. Let me draw the picture and then I'll explain it. this first thing is supposed to be the set of all log linear models, okay, which is the same as the set of all multinomials. Every multinomial can be expressed in log linear form and so on. Then there's a subset of these which are called hierarchical log linear models. Now, for those of you who are familiar with Bayesian inference, there are things called hierarchical models. This is not the same use of that word. Okay, different use of the word hierarchical. I'll explain what it means in a minute. Then there's a subset of hierarchical models which are called graphical log linear models. Okay, let me now explain what these are. Let's see. So, which one should I start with? Yeah, so I'm explaining this at the bottom of page 15. Let's start with graphical, since it's a graphical log linear model. So remember, I gave you a rule for drawing a graph here, but notice the graph wouldn't have changed if I'd taken out this term, right? So when I draw the graph, I can always ask, are there other terms I could have added in here without changing the graph? In other words, what's the largest model consistent with the graph? If it's not the largest model consistent with the graph, then we don't call it a non-graphical model. And otherwise, it's a graphical model. So I said that at the bottom here. A graphical log linear model is a log linear model for which the parameters are non-zero if and only if that variable is a clique in the graph. That is, let me say it in better terms. It's really just saying, didn't I give an example? I'll make up some examples because apparently I didn't put them in here. But it's, this is a non-graphical model if I do this. Because I ask, can I add any terms without changing the graph? Yes, I could add this in. So that would be a non-graphical. But once I put this in, now I ask, can I add any more terms in without changing the graph? The answer is no. So this is called a graphical log linear model. It's sort of the maximal model consistent with its graph. You couldn't add any other terms in. What that means is the graph is implying these conditional independence relations, but it's not implying any other constraints. So if I said beta 1 is 0 in here, that doesn't change the conditional independence statements. The graph is the same. But it is restricting the set of distributions that you can represent. What is that restriction? It's not a restriction you can express in the language of conditional independence. It's just some other restriction. It's just saying, originally, here's the set of all multinomials. When I write down this model, I'm saying, oh, it's in some restricted class. This is the set of all multinomials, in fact, that have this graph. This restriction to the multinomial corresponds explicitly to a conditional independence statement. If I set beta 1 equal to 0, I'm saying, actually, it's in a smaller set. And what is that set? It's just the set where beta 1 also happens to be equal to 0. But it can't be, that restriction can't be expressed in terms of any conditional independence statement. There's other things you can say about random variables besides dependence and conditional independence. So it just happens to have other restrictions. Some people will insist that when they use log linear models that they be graphical, so they'll force these terms to be in. You don't have to do that. There's no reason why nature forces the beta 1 to be in there. It doesn't hurt you in any sense, because if I put beta 1 in, and if it's not there, the beta 1 hat will just be close to 0. You'll consistently estimate it to be close to 0. So this is all about whether it's representing things other than what you want. So for example, if I had, it's a bit hard to show here, but this one's too small to show you. I'll show you, let me show you some more examples. For example, if a second order term was 0, that's just saying, we would just say in statistics that second order interaction is 0, that the two variables are not interacting together to affect the probabilities. But it may or may not correspond to a conditional independence. So that brings me to actually the next thing, which is a hierarchical model. A hierarchical model is simply means that and if it's not hierarchical, by the way, it can't be graphical. So that's why I drew it. Did I not have a picture of that somewhere? Well, let's redraw it. Again, this is all log linear. These are hierarchical. And these are the graphical models. Hierarchical just means this, that any time a set of indices is contained in another set of indices, that the corresponding betas here are 0 must mean that the larger set of betas is 0. So let me just give you an example of this. Let's go back to 3 variables. That's all we really need, I guess, to illustrate this. And suppose I tell you the model looks like this. The true distribution has the following form. Oops, this is supposed to be x1 times x2. Let's write this correctly. This is x1 times x3. Okay, there's the model. I'm telling you this is the true distribution. Notice what's missing, beta 1, 2, 3. So the only term missing here so the first thing is, let's start with this model. What's the graph? What conditional independence statements are implied? It's fully connected. There aren't any conditional independence statements implied by this graph. Okay, fine. Now let's ask the next question. Is it graphical? Is this a graphical log linear model? No, because I could add another term, namely this one, without changing the graph. That doesn't really mean don't interpret that to mean there's something wrong with the model. It's just a property that this model has, that it's not the largest model consistent with this graph. That's all it means. However, it is hierarchical. What do I mean by hierarchical? Well, let me give you an example of one that isn't hierarchical. That's not hierarchical. Because to be hierarchical, if beta 1 is 0, then beta 1, 2 has to be 0. If beta 1 is 0, then anything containing beta 1 has to be 0. So actually, if beta 1 is 0, beta 1, 2 has to be 0, and beta 1, 3 has to be 0. Now, why do we care about whether it satisfies the hierarchical property or not? One reason is just, this is sort of an old-fashioned reason. People thought, I don't know why they thought this, it didn't make sense to have what's called a main effect, which is what these are called, to be 0, and have a interaction effect to be not 0. I don't know why they thought that. There's no reason. I mean, this is you can create it. This is a well-defined distribution. So there you go. There's an example of a real distribution where the first order term is 0 and the second order term is not 0. I don't know why people think that somehow there's something wrong with that. There isn't anything wrong with it. Mathematically, it's a perfectly well-defined model. On the other hand, if you're doing things like forward regression, if you're building up this model in a forward stepwise way, it's often the case that people will start by putting in the lower order terms and then putting in the higher order terms, and it makes the model search easier if you assume the model is hierarchical. Because if beta 1 doesn't appear, then when I go to put in the second order, I don't have to look for beta 1, 2, or beta 1, 3. So sometimes people make that assumption, and a lot of software makes the assumption that you're only interested in the hierarchical set of models. Okay, so I'm not suggesting you should do that. I'm just pointing out that that's a type of model, a type of log linear model, and that there are types of software that enforce that, but there's no reason why you have to. All right. Good. So there you go. Let me think if there's anything else I need to tell you about log linear models. Well, so I haven't talked about really the high dimensional case. So if the dimension is fixed and n is fairly large, fitting these things is fairly easy because we're just going to do maximum likelihood estimation. You're going to get out a bunch of beta hats. It's going to compute the Fisher information for you, so we can use everything we used in 705. You can use the score function. the Wald test. We didn't do square. The Wald test, for example, or likelihood ratio test to test whether coefficients are zero. You can do model building. We talked a little bit about AIC, for example, in 705. You could build a model like adding terms one at a time and use the AIC criteria to decide how big a model and so on. These things are all built in, again, to R and I'm sure to MATLAB. I would be surprised if it wasn't there as well. If you want to build a high-dimensional version of this, and I don't want to really get into this, but it's pretty obvious, I think, what you have to do. You add an L1 penalty term to the log likelihood, and then you have a high-dimensional version of this. And I was going to tell you the R function that does this, the high-dimensional log linear models. It is called, I'm having a senior moment because I can't remember. The name is not intuitive. Does anybody know? You remember? No? Okay. Well, anyway, I'm forgetting the name. There is a nice function in R, very fast, which will take linear models, log linear models, logistic models for that matter, all kinds of models, and it'll do maximum likelihood, whatever, least squares if it's continuous variables, but it'll add in the sparsity penalty for you and find the parameter values and so on. So it's very simple to do these things.
There's one question that couldn't get through.
Okay.
The hierarchical one, it seems that hierarchical model can express those that are in the third circle, not in the second circle. And we discovered that. Yes. So somewhere outside.
There are things that are not hierarchical models.
But can hierarchical model express them?
No.
But in this case, it seems that if we add our x1 term, then we can express it.
But then it's not. But then it's back to being hierarchical. Yeah. Now these are strict subsets. Okay. So, any other questions about log linear models? They really are just again a re-expression of the multinomial in a way that's convenient for getting conditional independence statements and hence for drawing graphs and things like that. But now what you've seen is that we've talked about how to do the multinomial, the discrete case. We've talked about the normal, the continuous case. There are some papers where you do mixed discrete and continuous. I'm not going to talk about that, but you can imagine that you could mix and match these things and try to deal with them simultaneously. We talked about doing non-parametric correlation graphs, but what we haven't talked about is there a way to do non-parametric conditional independence graphs? Well, the answer is in the discrete case, we just did it because the multinomial is the most general. It's every distribution for a discrete random variable. If you take the set of all possible distributions, it is the set of multinomials. So the multinomial case does do, in some sense, the non-parametric approach to finding graphs. But suppose we have continuous random variables, and I want to find the graph. I want to find. Let's remember what the way we're interpreting the graph is that it's missing edges that contain information. So if I have this graph, this is say x1 and x2, it's the missing edges. So I'm saying that x1 and x2 are independent, conditional on the other variables, conditional on x3 and x4. That's what that graph means. What other conditional independence statements can I read off there? Any other missing edges?
X2 and X3 are independent given X.
Yeah, x2 and x3 are independent given these two, and these are independent given the other ones. Missing edges have these. But how are we going to find this out? So presumably, one way to do it is now for every pair of variables, we need to do a conditional independence test. Are those two conditionally independent given all the other variables? So how do we do conditional independence testing? Well, it turns out to be really difficult to do this in general, especially when the dimension starts to get large. And so this is actually an area of active research. A lot of people are working on this problem. I'll just mention now a few approaches to doing this and some of the challenges. So let's just focus on, if we know how to get one edge, if I know how to do one test between a pair of, then I'd repeat that for all the other variables. So for now, I'm just going to focus on getting one edge that is x and y independent given z. So what you should picture here is that this is one scalar random variable. This is another scalar, but z is a vector. Z is an RD or something in general. Okay, and so now I want to know, how do I test this null hypothesis that they're conditionally independent? Now there are tests out there, I should tell you, but in a lot of cases it's not clear what they're assuming and when they work and so on. That's why there's a lot of research going on about this. So actually, let me mention what I should have mentioned this first. Maybe perhaps some sort of obvious thing to do would be, if you look at the, this isn't in the notes, but perhaps I should have mentioned this. What we're really asking is this. Is this equal to So maybe one thing we could do is density estimation. After all, we can always rewrite these. Let's rewrite this, actually. This is P of x, y, and z over P of z, and so on. So if I have a density estimate for the joint density, I can always integrate out x and y, and then that gives me a density estimate for P of z. I can take the ratio, and then I have a density estimate for this. And similarly here. So I could just make up some statistic that compares these things. So I could look at, for example, just to make one up, if I put in a density estimator here, maybe this statistic could be used. This is just comparing this minus this, and I'm just squaring it and integrating it to do it over all possible values. And in fact, in the reproducing kernel Hilbert space literature, there are certain test statistics. Some of them are actually, they don't write them this way, but they're essentially this or something similar to this. So that's one approach that people take. There's a lot of complications here because there's a tuning parameter to pick, the bandwidth. Not clear how to do that for testing hypotheses. There's another problem, which is if z is high dimensional, what do we know about density estimation? It's not going to work very well, right? Another problem is, what's the null distribution? How do I know when to reject this? And unfortunately, permutation testing cannot be used for conditional independence testing. So that's an important conceptual point. When I was testing whether x and y were marginally independent, and I had some data here, under the null hypothesis, I know that if I permute y, it doesn't change the distribution of my test statistic. So I could do permutation test. But if you think about testing, are x and y independent given z, think about this almost like a regression problem. We're conditioning on slices of z. And for every slice of z, if I had a whole bunch of x's and y's here, suppose I had a bunch of x's and y's here, I could do a permutation test of that for a fixed z, and I could do that for every z. Because that's what conditional independence means. It means once you fix z, x and y are independent. And if I had many x's and y's, sure, I could do a permutation test. But when we have continuous random variables, what do we know? If I plotted the x's and the y's here, I'm going to have, well, I made them come out even more regular. At any given slice of z, you're going to have 0 observations or 1. Right? That's the way continuous data are. There's nothing to permute. In other words, testing conditional independence is basically, morally, it's as hard as doing non-parametric regression in some sense, because you're doing slicing on some third variable, which is a high dimensional variable. So this is quite challenging. So even figuring out the distribution of the test statistic is hard, if you even have a test statistic. Okay? So I'll mention let me There are some attempts, though, to deal with this, and I want to mention a few of them. It's not going to be exhaustive by any means. So one approach, this is a kind of clever approach. This is actually by the same guy. Remember we talked about the tau squared statistic. It was tau star statistic, that was it. And it's the same guy who thought of this. And he noticed the following thing, that remember it's related to this fact. You know that if I have x is drawn from a CDF, say capital F, what distribution does f of x have? If I take the CDF evaluated at the random variable, yeah, uniform, right? So a similar thing happens with independence here. If I look at the CDF of x given z and the CDF of, let's call it g of y given z, so this, what is f of x z? I just mean here the usual CDF, the probability that x is less than or equal to x given z is equal to z. Then he showed that if x and y are independent given z, that implies that u and v are independent. Well, that suggests if I can compute these u's and v's and just run my favorite independence test on that, that's a way of doing this test. It's not the strong property. It's not if and only if, but at least it's something. Yeah?
Isn't that finding the conditional distributions? I mean, is that the thing you can't do anyway?
Right. So it's going to be very similar to this. In fact, here we go. What we're going to have to do is estimate this, right? So what we're going to do is we're going to define ui hat to be the advantage of, well, let me just write it down. So what am I doing here? These are not the usual empirical CDFs because they're conditional, but you can just do a kernel estimate of the CDF just like we do a kernel estimate of a density. In fact, I wrote, that's what those expressions are in the middle of page 17. It's just, you just do a kernel estimate of the CDF just like you do a kernel estimate of the PDF. So yes, it inherits all the problems of this, except for one thing. The test statistic is sort of obvious. Once we get these values, now it's just a matter of testing marginal independence between the u's and the v's. And there's even a nice theorem here, which I wrote down, which basically says that asymptotically, you get out, the test statistic you get out from this is asymptotically, as n goes to infinity, the same as if you actually knew these u's and v's, so assuming you can consistently estimate these things. So this is kind of a nice idea. I have to say, however, that his paper has a lot of examples where it just seems to work. We're talking about 4, 5-dimensional examples. So this is not a high-dimensional technique because we are doing some sort of kernel estimation. When I tried to do it, I had a lot of trouble. I didn't even put in the examples because what I found is you still have to pick a bandwidth. And I just found it, and maybe I just did it wrong, but I just found it incredibly sensitive to the bandwidth. So whether I got a significant p-value or not significant p-value was very dependent on how I chose the bandwidth. And I couldn't find any good way to choose the bandwidth. So maybe I just wasn't doing it well, but there seems to be a problem there.
Are these what are called copula methods?
Called what?
Copula methods?
It's similar to a copula. So a copula is when you take an inverse integral transform and convert things onto the unit cube. We're going to do a copula in a minute, actually.
Why do we call this non-parametric but the graphic model as parametric?
Well, if I did this now to construct the graphical model, that would be a non-parametric graphical model.
What's the main difference between this and the previous?
The previous one is we tested whether the partial correlation was 0. And that's sort of like a linear estimate. That's like doing linear regression. It's like doing linear regression versus non-parametric regression.
Why
Well, partial correlation is a lot like linear regression because it's only computing the linear correlation between x and y. It's ignoring any nonlinear correlation between x and y. Yeah.
Can you use the empirical CDF?
No, if you use the empirical CDF, this won't work. You're just going to get junk out. For exactly the same reason here, because there's no information really given each z. You need to do some sort of smoothing. Yeah.
Do you compute correlations using like distance correlation or tau star, and that be considered non-parametric?
Oh, that's a good question. I didn't include that. So there are some papers. You could do the following thing, right? Let's let theta be one of our, not like tau star, one of our non-parametric correlations, distance correlation, whatever. We could estimate this as a function of z. How are we going to do that? Again, we're going to have to do some sort of smoothing over z, though. And then you could look at this integrated over z or something like that and try to create some sort of measure of conditional independence. So there are 1 or 2 papers about that as well. I should have mentioned that. They all have these tuning parameters in them, and they all have the same problem, which is nobody knows the null distribution. So it's not clear when to reject the null hypothesis. Except for this one, where you use whatever your favorite marginal testing is. So at least here, the rule of when to reject is clear. But I don't know how to pick the smoothing parameter. So you see, you start to see here it's getting kind of challenging. And this is even in 4 or 5 dimensions. Now what happens when we have 40 dimensions or 50 dimensions? So let me mention a few methods that have been proposed. And actually, did I put in the Daniela's method? Let's see. I didn't put in. I'm going to tell you 2 methods, and then there's a third one that I left out. Actually, let me mention quickly the one that I left out, which is by due to a paper of Daniela Witten. Do you remember when we did high-dimensional non-parametric regression? One thing we used was SPAM, sparse additive models, right? Remember that? So, and remember I said one way to construct a graph was to do, in the linear case, was to do a sparse linear regression of each node on the other ones. So she has a paper where she just does SPAM. She does sparse additive models on each node on all the other ones and takes turns, and that creates a graph from that. Oh, it is there. Well, thank you. It's right in front of me. It's right literally on the page I'm at, so I didn't notice it. But it's such a short. I've somehow reduced it to 1 sentence. So it's right below my little table there on page 18. I said one idea is to do node-wise regression using SPAM, and the nice thing is there's the reference if you want to see it. But I'll mention 2 other methods. Okay. One of them is based on some work I did with John Lafferty and Han Liu many years ago. We call it the non-paranormal. So there's a bit of a joke there, because paranormal, means like ESP and stuff like this. This is the non-paranormal, and it's supposed to be non-parametric, and there's a normal still involved in it. It's actually goes by another name. Its official name, especially in the econometrics literature, it's called a Gaussian copula. Okay, this is another name for it. So that's such an ugly name. We renamed it the non-paranormal. Okay, but it's really a Gaussian copula. So what this is an attempt to do is kind of do the same thing we did for regression, which is when we did regression, we said, look, a fully non-parametric approach to regression, if you had d variables, would be to fit a function like this, say using a kernel method or local linear regression, whatever your favorite method is. But really, trying to fit a high-dimensional non-parametric regression is very difficult. So what we did was additive models. We said, let's compromise and take something which is in between being parametric and non-parametric. We took a sum of smooth functions. It's not as non-parametric as this, but it's more non-parametric than a linear model. And if D was large, remember we put a penalty on this so we could get it sparse. That's the SPAM, sparse additive model. And we thought, couldn't we do the same thing for graphical models? Do something that's in between fully parametric, fully non-parametric. And so this table kind of explains it here on page 18. So it's really just filling in a gap in this table because we have our parametric models and our non-parametric models, right? And then the way to think about it is the dimension can be low or high. Now, the regression world looks like this. If we typically a parametric low-dimensional model, it's just a linear model. Okay, and then for a high-dimensional model, we do something like lasso or some sort of sparse regression. For non-parametric regression in low dimensions, we just did the additive model like that, and then all we did is we added a penalty to that in the high-dimensional case to make it SPAM. An L1 penalty, remember? But then, so the idea was just let's just mimic that. For graphical models, we can do the same thing. So the typical parametric low-dimensional graphical model is just the multivariate normal. The typical parametric high-dimensional case was the sparse version of that, which was the Glasso. Okay, and here we're going to now just do a similar thing to additive models to regression things. So this will be the non-paranormal. Normal, okay. And then this will be the non-paranormal plus sparsity, plus a sparsity penalty. Okay. And as I said, it's really just going to be a Gaussian copula, as it's called. And here's how it works. Instead of assuming that the data are normal, we'll just slightly weaken the assumption. So it's not going to be, again, completely non-parametric. What we're going to assume is that there's some function of x that is normal. Now, if I left it like that, if I said there exists some function of x which makes it normal, that's actually a very general assumption. That would be pretty much non-parametric. Where the restriction comes in is we're going to mimic this restriction of the function being functions of single variables only. So this will be assumed to be a smooth function of x1, a smooth function of x2, and so on. So we're going to assume there exists smooth, in fact, for most of this, we'll make them monotone functions of each variable that would make it multivariate normal. Okay? And the interesting thing is that xj given xk is independent given the rest if and only if, oh, I forgot to say what the notation was here. So we're going to write this as non-paranormal. There's still going to be the parameters describing the Gaussian, but now there's a vector of functions. This is a whole vector of functions. But the interesting thing is this still contains all of the independence information. This is independent if and only if gamma jk minus 1 is equal to 0, where sigma here is the covariance matrix of f of x. In fact, yeah. So what does this mean? This means suppose somebody told you these functions. Suppose you knew these functions. Somebody says, for every variable, there's some function which, if I apply this function, makes it normal. and in fact makes it jointly normal, then all you would do is apply that function to your data and run the Glasso, or run whatever your favorite normal procedure is. So the only trick here is to find that function f. We can actually write down what this function f is explicitly, because we know that the probability that fj xj is less than or equal to t is, let's say, phi of t. But what is this? This is just the marginal CDF for xj at t. Sorry. Of f of xj. No, I wrote this down wrong. Is less than or equal to, yeah, this is fj. No, this is right. Sorry, let me rewrite this so it's clear. This is the normal, and this is just saying that after applying the transformation it's normal. Okay, this is equal to the probability that xj is less than or equal to fj inverse. Here I'm going to use the fact that I'm assuming monotonicity right now. Sorry, let me get rid of this. I'll leave that there. Okay, so this is now the marginal distribution for xj. Right? If I equate these two things now, just apply fj inverse, I get fj inverse of t is equal to, I think I did this wrong, but I think I have an extra inverse somewhere. But anyway, let's just see what happens. It's fj inverse phi of t. And I've got an extra inverse somewhere. What did I do wrong? All right, something's wrong. I'm just missing something simple. Because the answer is supposed to be, yeah, there it is in lemma 13. So I'll just put a question mark. I've got an extra inverse somewhere. But fj of xj is explicitly given by the following formula. We can go back and figure this out in a minute or next time, but I want to get the formula written down. The point is that there's a formula for xj just from the fact that we know that the normal transformation, that applying the function f makes it normal. And, oh, that's what it was. Yeah, so this should have been x, and then I applied f here. But anyway, let's just focus on this for a second. Under the assumption that it's a Gaussian copular or non-paranormal, the function fj we know has a specific form. Because we know that when we apply f, it has to be normal. And this is what the form is. This is a known function. This is an unknown function. But what do we know about the CDF? This is just a marginal CDF, a one-dimensional CDF. I can estimate it. So all I have to do to estimate this function is put in the marginal CDF estimator. There's only one small trick there, which is that you want to make sure this is never 0 or 1, because phi inverse of 0 and phi inverse of 1 go off to infinity. So it actually suffices to just modify the usual empirical to be the number of xi less than t over n plus 1 instead of n. Did I put that in, or did I put in? Yeah. So I actually put in a different version. So to prevent this from going to 0 or 1, there are two possibilities. This is plus 1. There are two ways to do it. One is simply to just, instead of taking the number of observations over n, you just add 1 to that. Or you can truncate the CDF. You can take the empirical CDF and truncate it at some number delta and 1 minus delta. And in the notes, I actually used the delta version. That's actually a little bit old because it has since been shown that you can actually just use the simpler thing and the theory still works. There's some theory behind all this. And the original paper, we had a particular truncation constant, but it turns out that's unnecessary. So let me try to put all this together now. We know that if we assume this non-paranormal assumption, there's some function for each variable. It's unknown. That has to be estimated. But there's your estimate of it. Fj hat of xj is simply phi inverse of, and this is just the empirical CDF with a small modification. So we actually have estimates of all the functions. And now what do? All you do is you apply this to your data and treat it as if it's normal. Just run the Glasso or whatever you do for the normal thing. And then there's some theorems that say that under certain conditions, that will consistently estimate the graph and so on. Yeah, I threw in some of the theory there. But I'm actually more interested in showing you how it actually works. Yeah.
So the reason that we use the Gaussian calculus is so that we get the correlation dependence relationship.
Yeah, although frankly, it was just because we knew how to do things with the normal. Now, how do we just sort of slightly generalize that? It's more a choice of convenience than anything else. By the way, you might wonder, how rich is this family? How rich is the family of non-paranormals? It's a set of distributions such that there is some, if I apply some function coordinate-wise, I get a normal. And that's pretty restrictive. It's definitely not fully non-parametric, but it's richer than you might think it is. In fact, if you look back on page 19, we plotted some of the examples of just trying out different functions and seeing what the densities look like. And you get out surprisingly rich family of distributions. You can get things with points in it, and you get sort of lumpy things with that look like mixtures, and you can get actually quite a variety of joint distributions. So it's not obvious actually what these joint distributions look like. They're quite rich, but they're not fully non-parametric.
Here, use that formula, you get every fj, xj is normal 0, 1. Is that,
Asymptotically, because
but what if you want to choose another parameters in the normal?
oh, so that's a good question. It turns out, I could allow a different mean and variance, for example, for each of the variables, but those are not identifiable parameters in the sense that I can always absorb those into the F. So that, in other words, if I assume this was some mean and some variances, it doesn't change the conditional independence statements. They're invariant under that. And since all we care about is the conditional independence, we can arbitrarily pick mu to be 0 and sigma to be 1. It's just like in spam, there was a constant we had to pick. Remember in spam, there was like a beta plus F1 plus F2 plus F3, a beta 0. This is not well defined because I could always include it into F1 or F2, so we arbitrarily took it to be y bar. It's a non-identified parameter. It's the same here. The marginal means and variance are not identified because if I shift one of the distributions, I can just accordingly define f to be the shifted function. So we just arbitrarily set these non-identified parameters to be 0, 1. It doesn't affect the graph, which is what we're interested in. So what happens, I wanted to just show you a couple of examples. Maybe I didn't put the good examples in.
Is there some kind of intuition for what kind of distributions can be represented as a
I find it hard to say actually, because when we started plotting these things, the shapes were very unexpected to me, and so I don't actually have a good intuition for it. And I should say, Han Liu has since generalized this to something called trans-elliptical distributions, where you don't even assume normality, you assume something about a distribution having elliptical contours, so which is even a wider family. So I don't actually have a good sense for how wide of this class of distribution is. It's something in between the normal and the non-parametric case, but it's hard for me to say exactly what it is.
So the only requirement is that applying a function to each marginal has to be normal. It doesn't mean that the joint has to be.
That's where the assumption comes in, right? Because of course, every one-dimensional variable could be transformed to normality. We're making the assumption that if we do that, it makes the whole joint approximately normal.
So you can't have any standard linear interval with the correlation structure. That's true.
I didn't quite.
So say you've got just a 2D normal with some correlation between the two. And the marginals would each be normal, but that's not necessarily the joint, right?
That's right. You can't recover every joint distribution that way. Yeah. That's sort of what's called, basically this is the copula assumption. So I thought we included a really, I think the notes were getting too long, so I took it out. But let me just tell you, because we did a lot of experiments with this just to see how well it works. And the interesting thing is it works much better than I even expected it to work. What I mean by that is, if we fit this to normal data, suppose the data were actually normal, then in principle the Glasso should beat the non-paranormal because it's assuming normality. We never found that to be the case. There never seemed to be any loss of efficiency by actually doing this, even when the data were actually normal. On the other hand, when the data were non-normal, this non-paranormal seems to do a really good job of doing a reasonably good job of getting the right edges, even if the model was not exactly correct. Whereas the Glasso tended to always put extra edges. Somehow I think it was trying to compensate for the lack of normality somehow by putting in extra edges. It's not clear. But very often we found slight departures from normality would lead to very dense graphs, whereas this method would lead to much sparser graphs. And so these are just empirical observations. They're not theorems. I can't prove that. It's just an observation that it seems to work really well. But again, there seems to be no loss in doing it. It doesn't seem to ever hurt the procedure. So that's one way to try to deal to some degree with the non-parametricness. There is, I've spent too many lectures probably on graphical models, but so I'm going to skip some of it. There's an extension here on page 21 called the skeptic. I have to say, at some point, stop making up names for procedures. I didn't make up this name. It was, I think it was Han or John. Spearman-Kendall estimator preempt transformations to infer correlation. That's a real stretch. But basically, it shows, what this does is it shows you can robustify this and use non-parametric correlations like Kendall's and another one called Spearman and still correctly get the edges of the graph in this model, and in fact for this wider family of models that are called transelliptical. But I'm not going to go into that. Okay, so there's extensions that are even more robust than this. The robustness, by the way, I have to warn you, the robustness here is critical. That outliers can really kill you in all of this stuff. So John Lafferty, who did this work with, he actually did a sabbatical at a hedge fund, and he actually used this stuff in the hedge fund. He couldn't tell me all the details. It was one of those things that if he told me too much, he would have had to kill me, or sue me or something like that. But he did say it worked pretty good for whatever it was they were doing. Except he said the big issue in all of these things for fitting high-dimensional graphical models was outliers. That if there's outliers in your data, it can really wreak havoc on whatever procedure you're using. So just keep that in mind. Question?
Actually, two questions.
Two questions.
The last thing you said, so just to be clarifying, so we never actually have to explicitly estimate the joint CDF of the transform. We never actually have to estimate that.
We are, in the sense that we're applying the estimated function f to each variable, and then we do estimate the correlation matrix.
But with the last of it, right?
Yeah.
Okay. And then the other other question, what was the last thing you said before my first question? The question about
Outliers?
outliers, right? So that's outliers. So that's going to influence the transformation, right? So,
Yeah.
So it's not like you can check them by the Mahalanobis distance or something on the Gaussian.
Yeah.
It's an outlier with respect to the original distribution.
In fact, a general problem is finding outliers in high-dimensional data is actually quite a challenging problem in itself, yeah. But I don't know what he did to find it because he couldn't tell me. All right, so I think let's finish up here. I mean, there's a lot more stuff in here. It's a long set of notes, isn't it? So I think I'll just tell you this one more method and then forget the rest of the notes because you're probably getting tired of graphical models. There is some other interesting stuff here about faithfulness and other things, subtle issues about graphical models, but we don't need to get into that. I'm just going to finish up right now by telling you one more method. Then I think you're saturated with graphical models, and then next week we'll move on to dimension reduction. There's some cool stuff there because we're going to talk about random projections, which is really cool. So let me just mention one more method you can do, which is to use a forest. Now, I want to avoid confusion. This has nothing to do with random forests that we talked about for classification. Maybe we should have some rule that once you name something, other people can't use the same names, but the names already existed. But it's a very simple idea, and it's a different way to go non-parametric. So what did we just do? We said we're going to try to be a little bit more non-parametric by applying these one-dimensional functions, but we're still letting the graph be any graph. But there's a different approach which says let's be completely non-parametric distributionally. We're not going to make any distributional assumptions now, but we're going to restrict the graphs that we can fit. And the graph is going to be a forest. A forest just means there's no cycles. So trees are examples of forests, or disconnected trees, whatever. You can think of them as trees or sets of trees. There's no cycles. So what's going to happen is if the real graph looked like this, when we do this method, what's going to happen is we're going to end up killing one of these things because that's not allowed. But the beauty of forests is, here's a nice theorem. If I have a distribution, an arbitrary distribution now, with a graph, which is a forest, then it turns out that the density has a very simple factorization, that you can always write the density as the sum of the the product of the marginals, and then the product over the pairs ij over the edges. Let's say I, j. These are just the edges. So this is this pair, this pair, this pair, times these bivariate marginals. The amazing thing about this is I never need to know more about the distribution to find the graph than the bivariate marginals and the univariate marginals. So what we do to fit these forests, there's various approaches you could take, but you first estimate all the univariate marginals, you estimate all the bivariate marginals, but you have to decide which edges go in here. Okay, and so there's various ways. How do you decide which edges to go in? There's various ways you can do it. In the reference here of our paper that I'm referring to, we did it in an information theoretic way, which is we say if I give you an arbitrary distribution and I say which forest best approximates the distribution in terms of Kullback-Leibler distance, then it turns out there's an algorithm called the Chow-Liu algorithm for actually doing that, and it goes like this. It's a very simple algorithm. It's a greedy algorithm. It says compute the mutual information. The mutual information, don't know, in case you don't know, is like a non-parametric correlation. It's another measure of non-parametric correlation, basically. It's just the distance between the joint and the product distribution. What the Chow-Liu algorithm says is find the pair with the highest mutual information, which is, again, just think of it as highest non-parametric correlation. Connect those first. Now keep going. Find the next pair with the highest mutual information, connect those. The only rule is if you form a cycle, throw that away and keep going. And provably, that gives you the best forest approximation to the distribution. That is, the best density of this form, which is closest in Kullback-Leibler distance to the true distribution subject to being a forest. And so, in practice, the way we did it was we took half the data and got all of the density estimates, and then use the other half of the data to estimate the mutual information, which there are many different ways to estimate the mutual information. One way to do it is to plug the density estimates in. That's actually not necessarily optimal. There are estimators designed specifically for estimating mutual information. The point is, for every pair of variables, though, you have a number, which is you can think of as the non-parametric correlation, and now you just build up the forest. It's very simple. It's a very simple, fast algorithm.
So when do you start?
By splitting the data, it's important that you use part of the data for estimating the density and part for estimating the mutual information, because the mutual informations will actually, the total, what will end up happening is you'll actually get, the score will not improve after some point. So another way to think about this, let me just say it a different way. You can fit the full thing and end up with a tree at the end. Then you have some score for how well you're doing. In fact, you could even use cross-validation, for example, to choose how big a tree to build, or how big a forest to build. So there is a tuning parameter there. What ends up happening in practice, this actually works really well. I like this much better than the non-paranormal. But you do, it's much more non-parametric, but you do get this problem, as I said, which is that if the true graph, and we've seen this in many simulations, so if the true graph, looked like this, you're always forcing it to be a forest, so you're always breaking this graph. And an interesting question is there a post-processing way to find the lost edges and replace them? Maybe you could fit this forest, then maybe you could do something afterwards, maybe using, I don't know, some sort of non-parametric thing to try to find lost edges. But I don't know the answer to that. Maybe there is a way to do it. I don't know. And it also suggests, by the way, maybe mutual information. Frankly, I wasn't that happy with using mutual information. It's a very hard thing to estimate. But we know lots of other non-parametric estimators of correlation. So you could presumably just do this with other non-parametric correlation estimators, at least heuristically. Sorry?
So the point of this is that it's an alternative to doing conditional data assessing, is that right?
Right.
So just testing the independence implications.
Yeah, somehow we've gone back to marginal testing, but we're claiming it's an approximation in some sense to the overall graph, except.
Well, I'm talking about the post-processing.
Oh, yeah, that's why I don't know how to do it. Right. And let me just show you it's a beautiful picture. How much time do I have enough time to at least show you this picture. Now, I didn't print it out in color, so it doesn't look so beautiful. What these are stocks. So I'm about to tell you how to get rich on the stock market. No, I'm not. Don't do this and lose money and blame me. This is actually I had many pictures like this, but this is one of many plots that just shows you what the fitted algorithm looks like. In fact, I put the wrong one in because this was assuming Gaussian. It's the non-parametric one I meant to put in, but they all ended up looking pretty similar. The cool thing was these stocks come from different sectors, like agriculture, high tech, whatever. We didn't use that information when we built the graph. Then afterwards, we colored in the nodes according to the sectors, and it just came out beautiful. Does anybody have the color version here? Am I right? Did it look pretty beautiful? Yeah, it looks pretty good, doesn't it?
What is red and what is green?
What is red and what is green? Oh, we didn't. I'm sorry, I didn't put down what they were. I don't know. Yeah, they're just different sectors. I didn't say what they were. Don't go buying these stocks or anything like that. Anyway, that was just an example. Yeah. That's a really, really good question. So if I'm going to do these methods, is the bootstrap valid for something like this? There might be a way to make it work. I hadn't thought about that. I'm going to say maybe. You can certainly do it. And at some exploratory level, I think it would give you an idea of the variability. Whether it's valid in some sort of mathematical sense, I'd have to think about that, actually, because there's a lot going on here. It might be. Yeah.
Instead of just
people consider like a small mixture of forests or something like that?
Yeah, so actually, I'm surprised that I haven't seen much work on that. Marina Mila, who's at University of Washington, for her thesis, this was, when she was a student quite a while ago. Not that she's old, but this is quite a while ago. Her thesis was on mixtures of trees. So she did do it in her thesis work, but I've never seen somebody pick up that work again. Maybe it's there. It's hard to keep track of everything that's done these days. But that's a very good question, because mixtures of trees would be a nice extension of this that would be much more expressive than just trees. Yeah, I think that's an interesting idea. Okay, yeah.
Is the result from this first always deterministic, or would it be, for example, all of them are circles or squares, and random edges are being removed?
Yeah.
Would they be random?
Yes, so when we did simulations, sometime this one would disappear, sometimes this one. It would always be very close to the true graph, but it's hard to say which edge is going to get lost.
So you montage the end result, and you do it like many times as possible, and then you montage the result together?
Oh, so maybe, yeah, so that would be an interesting idea. Maybe to do some sort of bagging,
Yeah.
right? So fit this thing and get the tree. Now, like bootstrap the data, refit it, get another tree, and then sort of do some sort of combination of these and putting them together. That would be a great paper for somebody to write. Somebody should do that and write a paper showing that recovers some of the missing edges with high probability. That would be a great paper. One of you can do it, right? Yeah, you have all the tools now, so that would make a fantastic paper. Call it, it would really confuse people, because you could call it bagged trees, and they'd be thinking you're talking about random forests, and they just confuse the hell out of everybody. But it would be a very interesting thing to see if that worked, actually. That's a really, really very nice idea. So again, we're going to go to dimension reduction next week. Let me just tell you, if you want to read more about this stuff, maybe you're sick of it by now, but section 4 just talks more formally about these properties of graphs that have kind of been very loose about, which is the Markov. What are these graphs actually representing? There's things called the Markov property and the clique decomposition of graphs. So some of you are already familiar with this stuff. If you're not familiar with it and you'd like to know it a little bit more about it, it's there. Enjoy yourself over the weekend reading it. There's a section on faithfulness, which is a really, really subtle but interesting point. If you're not interested in it, you can just skip it. And I posted the notes on dimension reduction. So we'll do dimension reduction. We're going to do that. We're going to do random projections. We're going to do differential privacy, I think. And then maybe some random matrix theory. We'll see what's we're running out of time, so we'll have to see what's left. Any questions? Okay, then have a good weekend. I'll see you on Monday.